We live in a time of global transformation. The Energy Futures podcast explores how we can accelerate the expansion of clean energy technologies and reduce our reliance on fossil fuels. From heating and cooling our homes to moving around our planet and beyond, we bring together researchers, scientists, business leaders, and communicators to exchange knowledge and try to answer one important question. How can we create a sustainable energy future for all? This podcast is produced by Energy Futures Lab of Imperial College London.
In today's episode, Dr. Aidan Rhodes speaks with Dr. Nadine Moustafa for an in-depth discussion on carbon capture and storage, otherwise known as CCS. We'll break down what CCS is, how it supports the energy transition, and explore the latest research innovations in this crucial technology for achieving zero carbon emissions.
Okay, so today we're talking about CCS, which is an acronym often heard in the energy sector. We hear people say CCS a lot. CCS will either solve our problems or contribute nothing. But what is CCS? And for those of you who don't know, we're going to find out what it is, what it can do, and what it can't do. So I'm going to ask you first, Nadine, what does CCS stand for?
Okay, so the acronym stands for carbon capture and storage, and essentially it's within the name. You capture the carbon dioxide from point sources or from the atmosphere, but that's another thing. So let's just focus on point source. If you capture the CO2 from a point source, that could be a cement plant, for example, a steel plant, and then you compress that CO2, you transport it, and then you store it underground forever, essentially. And so that would mean that you're not releasing the CO2 into the atmosphere.
So you're using the same processes as we do nowadays to burn gas or even coal or do industrial processes, but instead of allowing the carbon dioxide to go into the atmosphere, we are capturing it and storing it away where it can't.
Exactly.
Yeah. So you work in CCS, do you?
I do, yes. My PhD massively focused on the carbon capture part of it, so not the transport or the storage part of it. And I worked with certain solvents, essentially. But I think just for background, CCS, yes, it's a relatively new technology, I guess, that we're trying to deploy a lot now, and we need a lot of it now. But the concepts of the technology is not new at all. And so if we think about natural gas sweetening, and so essentially natural gas, when we get it, we get some form of acidic gas in it, so hydrogen sulfide, which shares similar properties in the sense of that CO2 is also an acidic gas. And so before natural gas can go to our homes, for example, in boilers and stoves and whatever, we had to remove this hydrogen sulfide gas because it wasn't safe. And so to do that, we've done the capturing of this hydrogen sulfide. And essentially what we're doing with carbon capture and storage is using this technology that we've already been doing for decades. The difference is, though, that CO2 does not have, now it's starting to, but essentially initially it didn't have an economic price. So it didn't count as, just like purifying something that you're selling or whatever, which we do in a lot of different industries. It just counts as an extra thing you need to do. And absent policy and regulation and carbon tax and so on, is just extra money that you would do for no reason.
Yeah, so basically what you're saying is we've had, I guess, the concept of capturing gases such as carbon dioxide for a long time, but there's been no point in capturing carbon dioxide from the economics.
Exactly.
Economically, it's valueless. But you're saying that's changing now? Are people working out what to do with CO2?
Yeah, for sure. So there's carbon tax. So there's a lot of different things actually happening. So in terms of, they call them market-based measures. So that could be a carbon tax, for instance. So for every ton of CO2 you emit, you have to pay a carbon tax. It could also be a cap and trade program, so like what we're seeing in the emission trading scheme. And essentially that would mean that each company has a specific allowance of CO2 emissions per year, and that decreases with time, and that decrease is basically follows the net zero targets of the country. So for example, in the UK, we have a UK ETS and different industries are involved in it. And so for example, cement is involved in it, and they would have to do things like CCS to ensure that they follow that trajectory and not pay carbon tax on the above, which would be more expensive.
Great. Okay, so let's take a step back. So can you explain the process of carbon capture and storage? So say we've got, for example, a natural gas plant, it's burning gas. Carbon dioxide is one of the gases which is being produced as the exhaust, I guess. So how would we get that carbon dioxide out of the exhaust and into the ground?
Yeah. So essentially each plant, so for example, if we're focusing on natural gas or cement or steel or whatever, each plant has a different flue gas coming out of it. And by that, I mean there's different concentrations of nitrogen, there's different concentrations of CO2, and then other gases. And so the first part of it is that if we just focus on the capture part, it's essentially a two-stage process. The first stage is that you run I don't know how many people are, remember their chemistry now, but essentially CO2 is an acidic gas, and if you run an alkaline counter in a counterflow, the CO2 within the flue gas at a certain percentage, let's say 10%, will react with the alkaline. And then now you have this alkaline that's loaded with CO2, and then you have a flue gas that can go to the atmosphere with very little or no CO2 essentially, and just like nitrogen and so on, which can be pumped into the atmosphere. That's fine. And then you have this loaded solvent or like alkaline, and from there you have to kind of regenerate it, right? You're not going to be putting fresh solvent every time. That's just not economical. And so to regenerate it, the reaction between the CO2 and the alkaline is reversible. So for instance, it happens at a certain temperature and pressure. And if you just kind of switch that, so if you increase temperature a lot more than the reverse reaction would happen, and you would get pure CO2 out. And then that CO2 comes out. That's the second stage. And then you compress it and then transport it. I have to say that's the most mature technology that we have now. And it is the most mature technology, one, because it's commercialized, but also because, as I mentioned, it heavily depends on things we've been already doing for decades. But there are other technologies happening. They follow more or less similar processes in the sense of CO2 is extracted in some way or another from the flue gas. But for example, it could be, instead of solvent-based, so instead of liquid-based, it could be solid-based, for instance. And there's quite a lot of novelties in terms of which solvents we should be using. So not just alkaline, like pure alkaline or whatever. Like there's a lot of different things that people are looking into.
So there's quite a lot of active research going on to, I guess, make the process more efficient, make it more, I guess, reproducible maybe, and are there any issues with the solvents and sustainability or environmental impacts which can be sorted out?
Yeah, for sure. I mean, I would say it's the same for like any material you use in pretty much any industry. So in terms of the amine itself, so okay, I'm just saying amine because that's what my research was on, but there's a lot of different solvents. But usually you would have to look into things like degradation, for instance, because once they degrade, there are certain byproducts that you wouldn't necessarily want, and you have to kind of also start looking at, when they degrade, what products are they producing, how are you going to handle these in terms of, like, for example, waste handling and so on. But again, we have like so many years of experience on this, so that's not the biggest deal. But my research, for example, in my PhD was focusing on looking at the reaction mechanisms that are happening. So like really going in there and understanding the fundamentals of exactly what's happening. Because as I said, like, yes, we've been doing it for decades and decades, but it was with an economic output. So it's made sense economically. And so, we didn't need to know the nits and grits of it. Whereas now we need to kind of really make it as efficient as possible, really understand what's going on in all aspects of it, not just the capture part, or even the technology part. We need to know a lot more about everything, and so that we can deploy it at the scale that we need it to.
So let's talk about, you mentioned efficiency there, and how we're needing to work on it as much as possible. So how efficient are the processes? If we have, for example, a fossil fuel plant with CCS attached, how much does that affect the output of that plant?
So theoretically, the efficiency of CCS can go up to 99%. You can get to that if you want to. As in, you can capture 99% of the CO2 that's going out. Whether you want to get to that or not is different, because like obviously there's like a cost attached to it, and usually the cost from going from, for example, 80 to 99% becomes exponential. Again, as with any technology, like getting that last couple of percent is the most expensive part. And so then you get into CO2 removal for your residual emissions, which is another part of my research, and actually quite close to this, right? Because so CCS focuses on the carbon capturing from point source, so from a flue gas, whereas CDR, so carbon dioxide removal, technologies focus on removing CO2 from the atmosphere. And so essentially the point of that is that it'll be hard or extremely expensive to get that last, whatever percentage, which people usually term as residual emissions or hard to abate emissions. And so what we would do instead is we would, directly remove it from the atmosphere. But that's only after, we've done everything else we should be doing.
Yeah, absolutely. So when we consider, for example, the United Kingdom, what role do you think CCS is going to play in our transition?
So actually, UK has been a leader in a lot of this stuff. So for instance, when it comes to industrial decarbonisation, they've identified the different clusters, industrial clusters. And by industrial clusters, I mean that we know where our emission sources are. And so if we can cluster them to a certain geographical circle of some sort, then it would be easier to essentially connect them all and use this similar infrastructure, for instance, and so on. And that would mean that we can tackle our emissions in a, in the best or like a more optimized way. And then once we do those once we handle those emissions from the different industrial clusters, then we can focus on the harder emission sources, such as ones that are like distributed or in the middle of nowhere.
Yeah.
And so the UK has done that. They've identified their industrial clusters. They've done a lot of research on each industrial cluster. There's a lot of plans that come out from each industrial cluster. And then they also have the fact that they want to get one of those industrial clusters net zero by 2030, and then all the rest kind of follow
along
after the 2030s.
So where are these main industrial clusters located?
So there's the Teesside cluster, which is the one that will be net zero. There's the Humberside cluster. So they're located all over the UK, we could probably add a map. But usually, like they're located all across the UK, and some are in the east, some in the west. There's one in Wales, for instance. So it really, really depends. But they've been identified as where a lot of emission sources are grouped together.
Yeah, and these clusters are often on the coast, I understand. And I guess that makes it easier to send the carbon dioxide offshore to be stored.
Yeah, so there's actually a lot of research happening now about how are we going to be doing the CO2 transport networks. Because you can transport CO2 either by pipelines or by ships or by trucks. And again, the technology readiness level of those differ. So for example, for pipelines, it's quite high. And the reason is, again, we've been transporting gases through pipelines for decades. And so there's also, you can also repurpose natural gas pipelines into CO2 pipelines. Yeah. And then ships is a bit ships is not commercialized, so there's a lot of demo plants and pilot plants that are happening, pilot studies. And then trucks is a lot less commercialized, and usually would only really make sense in like very, very specific scenarios. And so mostly it would be ships or pipes.
Yeah, I'm guessing that trucks would not have the throughput required.
Yeah, it's very, very specific to very small scenarios, but usually it's like you ship it or you do it through pipelines. And again, that kind of involves a lot of like looking at the costs associated with it. Where are you going to be putting those pipelines? Can they kind of integrate to existing infrastructure? Should we instead be shipping it to a certain port and then using less pipelines? And so it's an optimization problem of some sort.
So I guess Would you say that the UK, because of our history in natural gas exploration and exploiting, basically, are we well positioned for carbon capture and storage compared to other countries due to this industrial knowledge?
Yes, for sure. There's a lot of transferable skills. So, for example, I mentioned the CO2 capture part, the CO2 transport part, but also the CO2 storage part. We have a lot of the offshore exploration skills that we can use for CO2 storage. So when it comes to CO2 storage, usually what you would want to do is geological storage, and people call that the like for like, in the sense of if you geologically store it, it stays stored there for like thousands and thousands of years, as opposed to other measures that some people are looking into. But if you do it geologically, there's unminable coal seams, there's depleted oil and gas reservoir fields, and for instance, in depleted oil and gas reservoir fields, we already have the infrastructure there, so it wouldn't even take that much effort. But also there's like saline aquifers, and again, there's a lot of research happening within that specific field, like exactly how the interaction is, the thermophysical aspect of it. And so there's a lot of research at Imperial that's happening with this, for example. Okay.
So there's a lot of work going on here. And I guess the big question here is, as a lot of these technologies are relatively mature, and there's been a fair amount of research going on, have we got to the demonstration phase for a full carbon capture and storage plant yet?
Yeah, so we're already capturing and storing CO2. So that's that's at least there. It is, however, a lot less than what we should be doing. Yep. So I think we're capturing and storing around 50 megatons of CO2 per year globally, not the UK, globally. And there's probably another 30 or so that are planned. But if you look at any scenario, whether that's from the IEA, so the International Environmental Agency, or the IPCC, so the Intergovernmental Panel of Climate Change, we need around 5 to 15 gigatons of CO2 captured and stored. And so that's like 2 to 4 magnitudes higher than what we're doing right now.
So we are talking about thousands of times more. We're less than a fraction of 1% of where we should be.
Exactly. And I think you'd see that in most of the technologies we need to reach net zero. And so I think it's like going to be fast paced from now. And one of the most important things that people always talk about is how can we get to the nth of a kind? Yeah. And by that, it means like, so at first of a kind is the first plant you would do. And that would mean that, you do quite a few things wrong, inevitably, because it's the first time you've done this. Your efficiency is not going to be that great. You're going to learn a lot, but then you can pass that on to the second of a kind and the third of a kind and so on until you get to the nth of a kind where you really, really know what you're doing, and it's smooth sailing from there.
Yeah, it's as efficient as we can reasonably make it, I guess, at that point.
Yes, exactly.
And I guess this is as you point out, a global industry, a global opportunity. So are there differences to how the UK would look at this problem as compared to other countries, or is this something which is very transferable across the world?
I think it's quite transferable. It's basically, okay, so there's quite a few different ways to do carbon capture. And my research focuses on post-combustion carbon capture. And by post-combustion carbon capture, it means that you can retrofit a carbon capture plant to existing plants. Which is really important because you need to kind of consider lifetimes of plants, which, can vary from like 20 to like 80 years or whatever. And so sometimes you really need to kind of maintain the plants you have because just economically it makes sense, but you would want to make them more environmentally friendly so you can retrofit it. Yeah. There's other ways to do this. So there's like pre-combustion capture and oxy-fuel combustion capture. I'm not going to get into these for now. But in terms of like the retrofitting part of it, there's a lot of knowledge that can be transferred for sure, because you can put that on like a gas plant, you can put that on a cement plant, you can put that on a steel plant, you can put that in chemicals. So it's pretty much any point source. And then if we look at carbon dioxide removal technologies, which are a lot less mature than CCS, again, there's a lot of knowledge transfer that can be happening. And when I say knowledge transfer, I don't also just mean technology. So I think for example, with the carbon dioxide removal technologies, just because they're a lot less mature, I think countries are looking at each other when it comes to like policies and how are we going to be doing that.
Yes, because presumably just removing carbon dioxide from the air would be a massive undertaking.
Yeah, I mean, thermodynamically, it's
very
it's
difficult.
not that easy. It's inevitable. We have to do it. We've been doing it in terms of like capturing some CO2. There's a lot of technologies out there. There's a lot of companies out there that are doing this, and so we're going in the right direction for sure. But then like once you do your reductions, you have to look into your removals. And I think one of the important things to look into is that, so we see now we've been doing CCS for a while now, and we've known it's important. And I think it's just acknowledging that, once we need the plants, they're not going to be up and running if we don't do anything now.
Well, exactly.
And so I think that's the same for removals. So we can't wait until 2040 and be like, okay, now we need to do removals for the last part or the residual emissions, and then suddenly expect the technologies to be there. Or like up and running.
Technology, as you point out with the nth of a kind thing, you'd take a long time not just to develop it in the basic research phase, but also to refine it actually in the field, to actually build it at full scale and then make it better and better and better.
Exactly. And also like the supply chains aspect of it. So the supply chains of the materials that you're going to need is something that I think, in a day-to-day as a scientist or an engineer, people don't consider, but it's definitely important. If we're going to commercialize this, you're going to need, this many tons of a certain chemical and so on. And so those supply chains are quite important to look into also.
So you mentioned retrofitting. So obviously we have industrial cement factories, steel factories, gas power plants. Is it easy to retrofit carbon capture and storage technology onto these existing plants, or is it easier to start again with a new plant designed from the ground up to capture carbon?
Depends on what you define by easy. So you can definitely retrofit into an existing plant. You can do that. That's been done. That's fine. You can also build new plants. That's another thing. So the only reason I say it depends on what you mean by easy, because it depends on a lot of different things. So financing availability. So do you want to actually build a whole new plant? But also, do you want to so that the plant you've already built, you don't want to just lose, right? You can't just shut it down. It just doesn't make sense. You've built that plant. You've put money into this plant.
Yes, exactly.
And so it will be operational for another 40 to 50 years. It makes sense that you would retrofit it, make it sustainable for the next 40 to 50 years. And then we can... So there's a lot of things that you need to do in terms of like how to get to net zero. And so some of it will be retrofitting what we already have, and obviously some of it will be that once we build new things, we should definitely be incorporating sustainability and environmental aspects into it.
And if you are a company which owns a cement manufacturing plant, for example, it presumably would cost a fair amount to put carbon capture and storage on there. So what are the options for getting that financed? Are we talking about carbon taxation, or should the government be directly subsidising, do you think?
So it's a little bit of everything. So generally it depends on the country, there's carbon taxes. There's also, as I said, the cap and trade program. So for example, in the UK, there's the UK ETS, the UK Emission Trading Scheme. And cement is one of those industries that's within that ETS. And so essentially they have a certain number of allowances of CO2 emissions per year, for instance, and they need to kind of stick to that. If they emit more, then they have to pay up for those extra emissions. If they actually emit less, they can sell the allowances that they have to companies that are emitting more. So it's a business model of some sort, and so that's what would make it better that's what would make it incentivizing basically for cement plants to actually input CCS or look at other options. I mean, they're not going to get to net zero just by CCS. They're going to have to do a lot of other different things.
Yeah. Obviously, because CCS, while it sounds important, is still just one of the many technologies we're going to need to go to net zero.
For sure. Like there's absolutely no silver bullet technology. Like there's there's just not one technology that's going to get us to net zero, and that's that. It will always be an energy mix, and I think it also depends on, you know, where are you doing this, what kind of materials are available to you, what kind of resources are available. So like, do you have access to water, do you have access to land, and sometimes, for example, when it comes to, like, I visited a couple of plants in the UK, sometimes, you know, like, which is something that I would have never considered in my lab sitting there and doing it. Sometimes they just don't have the space in the plant. They're like, okay, where are we going to build you know, vents or whatever to get our flue gas to the carbon capture plant? We don't have space.
Yep.
And so I think actually this is a great example of like where we should be talking to each other a lot more in terms of like industry and academia, but also obviously with policymakers, and just seeing, you know, where are we directing our research, where are we directing our money, and in terms of like the government spending, but also where are we directing the goals in terms of industry.
Yeah, and it's a really important point, as you say, we need to be a bit more joined up by this. Yeah. We can't develop the perfect system in academia in isolation and then take it to the field and realise they don't have the space, or they don't have the money, or some interaction would damage the plants in some way, things like this. So let's have you've been doing research on CCS for a while now, haven't you? So what does your research actually entail in a bit more detail? Because you talked about amine solvents earlier. Yeah,
so my PhD was about capturing CO2 into aqueous-amine solvents. And that mainly, I did some form of design of experiments, so like the best set of experiments that we would want to do to look at different amines. I looked at the, again, commercialized amines, so amines that we know a lot about relative to other amines, but also like there's like different categories of amines, so those are the kind of ones I looked into. And from there, I started changing different operational conditions. So, for example, temperature, mixing speed, and flow rates, and things like that. And that would essentially help us understand more about exactly what's happening. And in my research, that translated to the reaction mechanism. So, what kind of reactions are happening? And that's extremely important in quite a few ways. So it's important in the sense of, yes, once we understand reaction mechanisms, we can optimize this more so we can get a higher efficiency. But also the biggest aspect of, or like the most important part of understanding those kind of fundamentals is that in the two-stage process that I described, the second stage is what's most expensive. So regenerating the solvent so that you can reuse it is the most expensive part. And so there's a lot of aspects that go in there. So one, if you're degrading your solvent, that would mean you need more solvent, and so that's more expensive. But also, so once you know the chemicals, like the exact products that you're getting, then you can optimize your second stage essentially. Yeah. And so that's basically what my research contributed to in terms of my PhD. And then after my PhD, I focused more a bit about like the systems modeling part of it. And so I looked at the industrial clusters and what would decarbonizing them mean, essentially. And so what technologies would we use? But also then I started looking into the techno-economic part of it. So how much would it cost to decarbonize those industrial clusters? But also the socioeconomic part of it. So how many jobs will that produce, and what kind of GVA, so gross value added, will you produce by decarbonizing those clusters? And what kind of supply chain issues could we face? So what kind of things do we need, and how much of it do we need?
So this is basically, I guess, focusing on getting our ducks in a row so we actually have the supply chain ready to produce a rollout of this technology, that we have trained people ready to actually develop the technology,
exactly,
deploy the technology at scale. So from the jobs point of view, is this a sort of, because a fair amount of this technology, as we talked about, is related to the oil and gas sector, is it something that people who worked in oil and gas can easily transfer over to, do you think?
Yes, and a lot of projects that happen within CCS are actually started by oil and gas companies. And I think that gives a bit of a controversial aspect to it, because people associate CCS with oil and gas companies just wanting to continue what they do and emitting more CO2. And I think it's just important to realize that, okay, so other than fossil fuel, CCS is needed in process emissions. So that's inevitable. Things like cement and steel and so on. But also it's important to realize that we're not going to get to net zero tomorrow. And so we need, as I said, like there's no silver bullet technology. We're going to need pretty much everything that we have right now to get to net zero. And the way that will work in the next couple of decades versus like up until 2040 and then past 2040 and so on is going to be different inevitably. Like we're gonna have different needs.
Yeah.
And also I think so I know we're talking about the UK, but I think there's a lot of different aspects to different countries. So the UK is lucky in the sense of it can do renewables. So it can do a lot of wind, for example. Yeah. There are other countries that are lucky in the sense of that they can do a lot of solar. But there are some countries that just don't have that many options. They can't do renewables, for example, due to land availability or water availability. And if it's offshore, their seas might be a bit too deep. And so there's other technologies that they can start looking into, but they might face issues with public acceptance or like just changing and economic. So there's a lot of different perspectives, and I think the UK is quite lucky in the sense of they can, do a lot of this, and they could be leaders in like how to transfer this knowledge to other countries that will inevitably need it.
Yeah, no, it's a very interesting point here in the UK. We are very lucky to have natural resources, both in terms of wind, as you say, but also in terms of the actual storage sites for the carbon dioxide, because we can use old natural gas caverns under the North Sea, which a lot of countries do not have. And yes, absolutely, this could well be a growth industry for the United Kingdom if we develop it well. So I guess just to sort of round up and sort of move this towards conclusion, what are your sort of what are the interesting things to look out for in the next 10 years? What sort of projects do you see being completed? Where will people actually be able to see this technology being used at scale? I
mean, as I said, it is being used at scale and quite globally, actually. So it'll just be interesting to see the scale of how are we going to or the rate, how are we going to be scaling this technology? Just because, as I said, we're way, way, way behind. Again, we've talked about this. You don't build plants overnight. And so the rate at which we're going to be deploying this technology would be very, very interesting to see how we're going to be collaborating, how are we going to be transferring the knowledge from different industries, but also from different countries. What kind of policies will make sure that it happens? So, for example, in the EU, yes, they have the ETS, but for instance, it didn't promote the use of CCS, and so they've actually made a separate policy of CCS because they acknowledged that we need it, and no one actually ended up doing it, and they're just doing all the other easy things. But we're going to be, as I said, we're going to be stuck in a position where these plants are not just built overnight. We're going to need to start working towards it from now, and so they've done a separate policy for that. So it'll also be interesting to see the policies that will create the supply that we need.
So this is getting to the nth iteration, I guess.
Exactly.
Like understanding what we do wrong now in order to fix it in the future. So that's what we need to look out for. Okay, well, thank you very much for joining us. I guess just to finish off, if people are interested about what you work on and what Imperial as a whole is doing in this research, where can they find that out?
So I'm definitely reachable on LinkedIn, and there's also the Imperial profiles. And there's a lot of different researchers actually at Imperial that work on this. So I'm sure we can find a way to kind of link that.
Brilliant. Well, thank you very much.
Thank you.
Thank you for tuning in to the Energy Futures podcast. Here at Energy Futures Lab, we are dedicated to addressing global energy challenges through pioneering research, innovation, and advocacy. To learn more about us and the exciting projects we are working on, visit our website and follow us on social media. If you enjoyed this episode, please like and share and subscribe to stay up to date with our latest content.